Alright, we're starting chapter 6. This is a stereochemistry tutorial. So when we talk about stereochemistry, the first thing we're going to talk about, we're going to define some things called isomers. So they're different compounds with the same molecular formula. So they're the same molecular formula, but actually different compounds. Right? So the most basic one to understand is structural or constitutional isomers. Those are isomers whose atoms have a different connectivity. Stereoisomers, however, are isomers that have the same connectivity, right? The same bonds. The same things are bonded to each other, but in a different arrangement in space. There's a couple different types. One of those is enantiomers. These are like our hands. They're mirror images of each other. Another type is called diastereomers, which is a pair of stereoisomers that are not mirror images, and we'll talk more about diastereomers later. So isomers, again, two or more different compounds have the same molecular formula. So these are two examples of constitutional or structural isomers. So they're the same molecular formula, C2H6O. And what you can see here is dimethyl ether has, of course, this connectivity, whereas ethanol has this connectivity. Same molecular formula, C2H6O, but different bonds, right? Different connectivity. So these are structural or constitutional isomers. More examples are shown here. So C5H12, pentane can exist, right, as C5H12, or it could be 2-methylbutane. And obviously they have different physical properties. Another thing about constitutional or structural isomers, they always will have different physical properties, melting points, boiling points, things like that. C4H10O, tert-butyl alcohol versus isobutyl alcohol, just a 2-butanol. This is a fancy way of saying that, or butyl alcohol. You'll notice these are all constitutional isomers, same molecular formula, different connectivity. Different things are bonded to each other, and you get different physical properties. Another example, C4H8O, you get a ketone, an aldehyde. Here's an ether in a ring. Again, different physical properties, same molecular formula. These are called constitutional isomers. So they have different connectivity, a different constitution. Now, it's important not to confuse constitutional isomers with conformational changes. We've been talking a lot about conformational changes when we talked about ring flips and Newman projections, rotating about sigma bonds. Right? A single molecule have different conformations due to rotation about sigma bonds. That's different. Rotating about a sigma bond is different than a constitutional isomer. A constitutional isomer actually has different connectivity. Now, if you notice, these two ethers have the exact same molecular formula, but they have different connectivity. The bonds are different. It's not the same as conformations, which is just rotating about sigma bonds. So don't confuse constitutional isomers with conformational isomers. So we talked about constitutional isomers, but actually have different things bonded. But what about stereoisomers? Stereoisomers are different compounds that have the same connectivity, right? So the same connectivity, and the only difference is their arrangement in the atoms in space. Right? So one example is called geometric isomers. The same molecular formula, but different spatial arrangement due to the rigidity of the molecule. Good examples of that are alkenes, right? Double bonds. A double bond can be cis or it could be trans. We'll talk about how we decide one thing is cis or trans. In this case is when the two chlorines are on the same side, we call that cis. If the chlorines are on the opposite side, we call that trans. Very similar to how we named cyclohexanes. The interesting thing here, though, is these are geometric isomers because these two molecules have all the same bonds. The only difference is the arrangement in space of the chlorines on the same side or on the opposite side. Or you can think of the hydrogens on the same side or hydrogens on the opposite side. That's the only difference. Same bonds, just a different arrangement in space. And you'll also notice different physical properties here too. Different boiling points. Right? You can have different physical properties with these. So these are called geometric isomers. And we'll talk about how we name something cis or trans in a second. Another type of stereoisomer is called mirror image stereoisomers. This is when we talk about enantiomers. Like think about our hands, left and right-handed. Molecules can be left and right-handed. Right? It occurs when the molecules mirror image are non-superimposable. Our hands are mirror image of each other. You cannot make them impose upon each other exactly. They're always different. So, mirror images, we're talking about something called a stereocenter. They're an asymmetric carbon. There's no plane of symmetry in the molecules. That means these carbons are bonded to four different things. And their arrangement in space, right, with this molecule, they're mirror images of each other. I can't rotate this molecule in any way to make it exactly like this. Right? There are different arrangements in space. It's like our two hands. Then here, one slide back, where this sp3 hybridized carbon was bonded to 1, 2, 3, 4 different things, 4 different atoms. So that could become asymmetric and have a mirror image. So same example here, a molecule that cannot be superimposed on this mirror image is said to be chiral. So our hands are chiral. Right? They're non-superimposed on this mirror image. Their mirror images, our left and right hand are mirror images, and they can't be superimposed on each other. However, a molecule that can be superimposed on its mirror image is said to be achiral. So chiral molecules had sp3 hybridized carbons bonded to 4 different things. Now you'll notice here, this carbon is bonded to a bromine, a chlorine, and a hydrogen, 2 the same things. I can rotate this molecule to be exactly like this. This is not a chiral molecule. It doesn't have an asymmetric center. It doesn't have an sp3 hybridized carbon that's bonded to 4 different things. These are all bonded. The 2 hydrogens are the same, which is very different. So we're always going to be looking for these carbons. We're going to be looking for these carbons that are bonded to 4 different things to find those asymmetric carbons. So this is not an example of that. So you'll notice here, and they'll keep saying this, is that there's a plane of symmetry within the molecule. Right? It's showing the molecule in a couple of different ways. This is called a Fischer projection. Right? This is called that wedge and hatch we've seen before. But again, it's just another way of bringing this point home. We have an sp3 hybridized carbon that's bonded to not 4 different things, not bonded to 4 different things. So hydrogen is the same. So this molecule is achiral, and that is not an asymmetric carbon. Not. Right? So we're looking, right, for carbons bonded to 4 different things. That's what we're going to be looking for. sp3 hybridized carbons with 4 different things, of which this is not. So we call it achiral. So example of a chiral molecule, a molecule that has stereocenters or asymmetric carbons with no plane of symmetry, meaning an sp3 hybridized carbon bonded to 4 different things, right, can be arranged in a left-handed version and in a right-handed version. But these 2 molecules are different. They have all the same connectivity, same molecular formula. The only difference is their arrangement in space. Think about our hands, a left-handed molecule and a right-handed molecule. So we say it's bonded, we call these 2 isomers, or if we talk about these 2 molecules, we call them enantiomers. Right? They're mirror images of each other. Enantiomers are mirror images of each other, just like our left and right hands. A molecule can be a left version and a right-handed version. Notice the atom, right? Again, connected to 4 different substituent groups, right? 4 different substituent groups. We call that an asymmetric atom or stereocenter, right? A lot of times you mark them with asterisks, and molecules having these are always chiral. Having one, if you only have 1 stereocenter, you're always chiral. Right? So these are called enantiomers. sp3 hybridized, connected to 4 different things. That's called an asymmetric carbon or stereocenter. So this is super important. You can think about why this is important. Left and right-handed versions are very important, especially in drugs or for smelling things. The receptors in our nose, if you look at this, limonene, are actually chiral, are like shaking hands. So the receptors in our nose are both right and left-handed, so they would interact with a left-handed molecule and get a lemon smell, different than they would a right-handed molecule and get an orange smell. So we actually have different stereocenters will actually give us different smelling compounds. In drugs, our receptor side, this lock and key idea. Some drugs are safe, is a sedative, right? The other enantiomer, the right-handed version, causes cancer or teratogens and birth defects. So we got to be careful what kind of molecules we're using, and which kind of drugs we're using, just based on the right or left-handed idea. Right? Lock and key. The lock only wants the S. That's what the left-handed version will make a sedative. But if there's another lock that takes the R, the right-handed version, that could cause birth defects. So you got to be careful about this and why this is really important. So the first thing we're going to do, if we go to these stereoisomers, these enantiomers we're going to talk about, we're going to need to identify chiral atoms. That means we need to find sp3 hybridized carbons, must be sp3 with 4 different groups attached. Right, 4 different groups attached. Right there, anytime there's a CH2, it can't be a chiral carbon, asymmetric carbon, because it has 2 hydrogens. Or CH3 again, 3 hydrogens. So let's look at this carbon. This carbon has a bromine, It has a CH2 bromine. It has a CH2 bromine. These two groups, these two substituents, are exactly the same. This is not an asymmetric carbon. It has two of the same groups. You can see it here. This carbon, right? It's mirror image. This carbon has a bromine and a CH2 bromine and a CH2 bromine. Two of the same groups. It cannot be an asymmetric carbon. Now look at this. sp3 hybridized, CH2, a CH3, a CH2 bromine, and a bromine. This carbon has four different groups bound to it. Therefore, right, it can have an enantiomer, a mirror image. I can't rotate this anyway to get exactly this mirror image, right? I can't do anything with my left hand to rotate it to get to be exactly like my right hand, right? So this carbon is an asymmetric carbon, sp3 hybridized, four different groups attached, and it can have an enantiomer, right? A mirror image of itself. Another example down here. This is a chiral carbon, a stereo asymmetric carbon, because it's bonded to four different things: a methyl, an ethyl, a propyl, and a butyl. Whereas this carbon is bonded to a methyl, an ethyl, a butyl, but then another ethyl. So this cannot be an asymmetric carbon. There's not a chiral carbon, because it has to have four different groups attached. So we may have heard, or maybe heard from biology before, as D and L, when we talk about proteins and sugars, and that's this R and N system. So how do we actually say, how do I know if a molecule is left-handed or right-handed? How do I know if the asymmetric carbon we're looking at, that's sp3 hybridized, that's four different substituents on it, OH, a methyl, a hydrogen, and ethyl. How do I know if it's a left-handed carbon or a right-handed carbon? How do I know that? That's called the RS system. So it's a convention for naming enantiomers, right? Because it's super important. We got to know which ones we're using. So it's this Kahn-Ingold Prelog system. And I'll break this all down for us. But the priority is first based on atomic number that's attached to the stereocenter. And we always give we're going to rank. Essentially, we're going to rank the four substituents on the sp3 hybridized carbon. That's four different groups. We're going to rank all these things, and then we're going to look at it. We'll be able to tell if it's a R or an S, a right versus a left, right? And I'll walk through how we do that. But this is the system. We got to find the carbons first, look at all the four substituents, and then rank them, and then we're going to be able to figure out if it's an R or S, right? R for rotating to the right, clockwise. S rotating to the left. S for left as in sinister, like a left-handed people used to be considered, left-handedness used to be considered sinister, so that is why it's counterclockwise is S. R is to the right or clockwise. So one of the things we want to think about also is how do we draw these things. So there's a way of drawing things into something called a Fisher projection. So we're used to the wedge and hatch. The wedge means coming out, hatch is going away from us. This sp3 hybridized carbon, which of course has 4 different things. There's an aldehyde, there's an alcohol, an H, and another OH, a CH2OH. So it's bonded to 4 different things. But how do I turn this into something called a Fisher projection? Right? What I do is, if I'm looking my eyes right here, I kind of flip this on its side, and the H and the OH are coming out, and the aldehyde and the CH2OH are going away from me. A lot of times they'll draw it like this. They won't actually draw the wedges and hatches. They'll just draw it flat like this, kind of flat Fisher projection. You maybe see these as sugars. Sometimes they'll draw sugars like this and up and down and kind of this crosswise. But what it means is, I always like to think of it as a bow tie. The things on the horizontal plane are coming at you. Things on the vertical plane are going away from you. So it's just another way to draw molecules in 3 dimensions. You just got to be ready to see that and know when you see it flat like this, that means the stuff on the horizontal plane are wedged. Stuff on the vertical plane are hatched. All right, so this is another way to take something we've seen before and draw it in a different way. But you'll see this a lot, so be ready for that. Now what this leads us to is to look at, here's a kind of a daunting slide. So 12 ways of drawing an S version of one molecule. So that means a molecule that has a carbon, S2-butanol, that has a carbon that's bonded to 4 different things: a hydrogen, a methyl, an OH, and an ethyl. It's bonded to 4 different groups. How many different ways can you draw this? Right? This is all 12 of these are all the same way. You can see the wedge and the hatch. There's rotating things around, wedge and the hatch, lots of different ways. You can see a bunch of different Fisher projections, where you can draw it that way as well. So what it means is we needed a good way, right? These are all the same molecule. How do I know it's S? Right? That's the next part we're going to work on. Is what are the rules to do this, to actually rank these substituents and go from there. So we'll take this example and go to the next slide and see how this works. Alright, so I have an example here where we have a carbon, an sp3 hybrid carbon, that's bonded to 4 different groups: a hydrogen, a fluorine, a bromine, and a chlorine. What that means is when I've drawn these wedge and hatches in, I've either drawn the left-handed version of that carbon or the right-handed version of that carbon. The next thing we need to do is figure out how do we decide what that is. So we decide that by looking at atomic number. Essentially, the higher the atomic number, the higher the ranking would be. So in this case, I like to find the highest and lowest. The highest, in this case, would be the bromine. So we give that a 1, and I use red. For the blue ones, for the red, for the 1, the lowest rank would be hydrogen. That's the lowest atomic number, 4. And the next highest rank would be chlorine. And the third highest rank would be fluorine, based on their atomic number, right? Their atomic number. Now, if I look at this, like, okay, I've got my ranking done. Now what do I do? So now how do I decide if this is R, an R, or an S? What I want to do is I want to get the lowest priority group going away, wedged, going away from me. Once I get the lowest priority group going away from me, then I need to look at this and see if it goes 1, 2, 3. In which way is that rotation? Lowest group away, and I look at the rotation. In this case, 1, 2, 3. The rotation is to the right. So if I rotate to the right, that is called an R molecule. That carbon is R. So that's a counterclockwise, or that's a clockwise rotation. An S carbon rotates counterclockwise. And so let's see if I can draw the S version of this. Right, so what was that process again? I rank everything by their atomic number, 1, 2, 3, and 4. I want to get the lowest priority group hatched going away from me, and that's just, I set it up this way, nice this time. 1, 2, 3. When I do that rotation, that's to the right, that's clockwise. That means this molecule is a carbon, is an R stereocenter, the R enantiomer, the right-handed version of our hand, right? That's that one there. Now, what happens if I want to draw the S version of that? There. So what would this mirror image look like? Well, let's start. So we're going to draw the carbon. Its mirror image would look like this. And how did I do that? And if you took this, and they're looking in a mirror, right? The mirror's here. See how these are the mirror images of each other? Hopefully. So we do the same process. We got to rank the substituents that are on the carbon bond to 4 different things. So here in this case, the ranking hasn't changed. Still bromine 1, hydrogen 4, chlorine 2, fluorine 3. We want to make sure our lowest priority group is going away from us. So that's hatched in this case. And then we look at our groups that remain and say 1, 2, 3. They rotate to the left. Notice that rotation to the left. That is counterclockwise. So that means this carbon is the S carbon. So it's the enantiomer. It's the left-handed version, the sinister, rotating counterclockwise. Right? They're running counterclockwise there. So that would be the S version of this. All right. Now what happens if I make this a little harder? Now the hydrogen, the lowest priority group, is not going away from us. So we're going to do some mental rotation here or redraw it to make sure we get it right. Or we can use our model kits. Model kits can become very helpful here as well. But ranking's still the same. Find the carbon. Is it bond to 4 different things? Yes, it is. So let's rank those 4 things. Rankings don't change here. So bromine's 1, hydrogen's 4, fluorine's 3, chlorine's 2. So now what I need to do, I need to mentally either grab this molecule and look at it, right, in my head and see which way it rotates. So one way I could do this molecule, if I want. So this is difficult. This is not easy. Right? So I can look at this and say 1, 2, 3, and visualize in my head that this is, and see it, that this is the S version of that carbon. What I would ask you to do with your model kits, if you wanted to use model kits to be helpful, is I like to use the red, white, and blue version of this. To think about things in red, white, and blue, and then that model kits have red, white, and blue, and then have green. So I'm going to draw a model kit quick. So here I have drawn what one of our models looks like you're given in class. Red, white, and blue, and green. What I like to do to make this easier for myself is to use these model kits. And the way I use them is I will say, in this case, the way I will rank them based on these colors. So what's going to happen for this example, so my top group is always, I call that red. So the bromine is always going to be the red ball. In this case, the chlorine will be the white. The fluorine will be the blue. And the H will be the green. And I do this by 1, 2, 3, and 4, the rankings. Right? Red, white, and blue. That's how you understand. That's how you remember the rankings. 1, red, white, 2, blue, 3, green, 4. So once I've assigned the bromine, the top ranked one is always red. The second ranked thing, whatever it is always white. The third ranked thing, whatever it is always blue. The last ranked thing, whatever that is, in this case it's hydrogen, is always 4. That's green. Now what I can do with my model kit is I can actually, whenever I do that, I can grab these things and I can hold the model kit and see, does it look like this? When I'm holding my model kit, is the blue thing coming out at me? Is the green thing going away? Or when the blue thing's coming out at me and the green thing's going away, is the red up and is the white ball down, or the white rank thing down to the right? If it is, then you have the right version of this. Because the other model kit you should look like this. So your model kits, your models should be mirror images of each other. So if you look at this, one of these models, right, if I did the rankings, if I wrote the rankings on here, right, this was red is 1, white is 2, blue is 3, green is 4, red, white, and blue. If you looked at this, 1, 2, 3, lowest priority group going away, 1, 2, 3, this is a S. So one of your models should be S. The other model you have, if I do the rankings, red is 1, red, white, 2, blue is 3, green is 4. If I look at this, 1, 2, 3. Oh, sorry, this was 1, 2, 3. That's clockwise, my fault. This is R, my fault. That's clockwise. This one is S. It's the S version. Right, so the trick here is you first have to be good at ranking. You gotta be able to rank them. Then you're gonna look at your two models. Hopefully you have these two versions. Literally make these models so they look like this. So they're mirror images of each other. One will be the R, one will be the S. You can even label them. Right? R rotates clockwise. 1, 2, 3. Give the lowest priority group green in the back. 1, 2, 3. That's clockwise. The S version is 1, 2, 3 counterclockwise to the lowest priority group in the back. Let's practice this again. Alright, so here's another example. We have a carbon bonded to 4 different things, a hydrogen, an ethyl, an oxygen, and an iodine. So let's rank these. Hydrogen would be ranked 4th, lowest by atomic number. Iodine would rank 1, highest atomic number. Oxygen, 2, carbon, 3. Right? Oxygen has a higher atomic number than carbon. There's our ranking. First thing you gotta do is that. Then what you're going to want to do is go back to your models. Okay, so which one of these models in your hand actually matches up with this? If we say, right, according to our thing, 1 is always the red, 2 is always the white, 3 is always the blue, and then 4 is always the green. What you're going to want to do is take your model, right, one of these two models, which you can move, and you want to see, okay, I want the green and the blue in the plane. I want the green and the blue in the plane. Or another way you could have done is, I want the red going away and the white coming at me. And then when that's the case, one of these will have the blue up and have the green to the left. One of your two models will map onto this perfectly. Once you see which model maps onto this based on these colors and the rankings, you'll know you either have the S or the R. So I can do that in this case too. Right? So we could rotate this. To practice, I would tell you that this is a... Alright, so for this one, use it to practice your model. I'm getting this carbon to be R. Check to see if you can get that. One of the hardest things to do, gotta make sure you have the rankings right by atomic number. Make sure the rankings right by atomic number. Then you go red, white, blue, green. Your top one is red. Your second one is white. Blue is 3, green is 4. You map this onto your models, which you have. One is an R, one's an S. You wanted the red one in this case going away from you, white coming at you, blue should be up, green should be left. If that's the right one of your models will fit that. The other one will not. The one that does fit that, hopefully you already have that labeled R or S. That's when you want to pick. So let's look at the situation where, perhaps what if we had carbons? What if we didn't have so clear that, right? Obviously hydrogen has a certain atomic number, oxygen, iodine. What if we had carbon chains? How do we do these rankings? All right, let's take a look at another example. What happens if we have essentially the same atomic number bonded to our asymmetric carbon? So in this case, we have carbon bonded, right, to this. How do we rank these? How do we do the ranking of these? Again, it's about atomic number, but it's kind of like a card game. So we're going to go, right, first we got to notice this is an sp3 hybridized carbon bonded to 4 different things. So this is a carbon bonded to 3 other methyls. This is a carbon bonded to 2 hydrogens and a carbon bonded to 2 carbons and a hydrogen, carbon bonded to a carbon, a hydrogen, and an iodine. So they're all different. How are we going to rank these? So we go 1 bond out. Everything's a carbon, so there's no high card wins there, no high atomic number wins there. So we go 1 carbon out. So we're now all at this point. We're going to look at what these carbons are all bonded to, see what their deck is, and then the high card wins. So the first one, this carbon is bonded to a carbon, and a hydrogen. Right? This carbon is bonded to a carbon, and then a hydrogen, which we of course don't draw in. This carbon is bonded to a hydrogen, and another carbon. Again, be careful, don't draw those hydrogens. So its cards are carbon, hydrogen, hydrogen. So the highest cards first. Next carbon over is bonded to 3 carbons. The top one here is bonded to an iodine, right? Of course, it has a higher atomic number than carbon. Top card first, carbon and a hydrogen. Right? An iodine, a carbon, and a hydrogen, 3 carbons. Okay, top card wins. So we have an iodine versus a carbon, and a carbon. So that means this must be ranked number 1. That's the number 1 substituent, highest ranked substituent. And so this is done. 1. Now we look and say, okay, carbon, that's a tie still. So don't know yet. Carbon. Okay, carbon, hydrogen, carbon. This is lost. This is the lowest priority one then. This would be ranked 4th. This is ranked 1. Okay, so carbon, so we check that off. So they're still tied at carbon. H versus carbon. This wins. So this must be ranked number 2. This would be number 3. Right, according to priorities. That's how we rank them by essentially their top card always wins. Now remember our thing we did before. We did red, white, and blue. Red is 1. White is 2. Blue is 3. And green is 4. That's what you need to do. All right. Take your models. Find it where the green is coming at you. The blue is going away. Above is red. To the right is white. Take that and have it labeled RRS. We already have it labeled that, RRS. And whatever one maps on there is the correct one. That's your RRS molecule. So remember, you're going to want to label them RRS based on putting the green ball away from you and doing red, white, and blue. So one molecule should be R, one should be S. And you take those after ranking and you map those onto here. So there's one other ranking way I need to show you. That could be a little different. And that is this case. Alright, so here's our new case. We're taking a look at this. Now what happens if we have a hybridization difference? How do we do that ranking? So let's just do the one. Let's wait to do this one and do the other ones because we know how to do those. So again, we go out carbon, carbon, carbon. So it's all tied. The first bond out. Then we show their hands. So this one has a carbon, and a hydrogen. This one has a carbon and 2 H's. And this one has 3 carbons. Okay. Now how do we do this one? Well, we know it has it's bound to a carbon. It's bound to an H. So what we do is we say it's bound to a carbon twice. So we say it's bonded to a carbon, and an H. All we're saying is basically that there's a pi bond and a sigma bond. So we do 2 carbons and then an H. Okay, so let's do our rankings and see if we can delineate here. So everybody has a carbon at first. Carbon, carbon, carbon. This one has, the top one, has 3 carbons. That's going to win. That's going to be the high card. So that's going to be number 1. Sorry. Be highest priority. That'd be our red ball. Our lowest priority, maybe the easiest one to find, it would be this one down here. This would be 4. Now we got to decide how do we do this next one. So these guys are virtually tied. So we were at this carbon for each, the first one out. Now we need to actually go out one more. Now we're going to have to go out one more. Trying to find the highest thing possible. So we have to do this, we have to play cards again. So in this case, that carbon is bound to a hydrogen, and a hydrogen. So what about this carbon? What's it bonded to? Well, we always know we play 3 cards, so we know it's bound to a hydrogen and a hydrogen. We also work backwards when we have hybridization differences, sp2 hybridization, we work back. So this carbon is bound to a hydrogen, but it's also bound to that other carbon. Going backwards, those pi bonds, we work back. So we'd say it's bound to a carbon and 2 hydrogens. So of course, then when we look at this, well, hydrogen versus carbon, this one wins. That's the winner. And so in this case, this will be ranked 2, and this will be ranked 3. All right, now you want to take your model out. You'd want to have the red up, white to the right. Coming at you is the green. Going away from you would be the blue. Whatever model that would be your RRS, and that would be the correct one, whatever version that is. Just to reiterate, I want to practice that again, maybe show you here. So just to reiterate here, what I'm trying to map on here is you should make your models, so you should have 2 models just like this, exactly like this, mirror images of each other. And what you're going to do is, right, take this and map it onto this ranking, according to the red being 1, white ball being 2, blue being 3, green being 4. But first you need to make sure you label your 2 atoms, your 2 models. So in this case, if it's red, white, and blue, red, white, blue, that's going counterclockwise. The lowest ranked thing is away. That's going counterclockwise. This would be your S model. The other one, red, white, blue, that's going clockwise. Lowest ranked group is away. This would be your R model. You should have an R and an S model. You have one of each. You're going to map it onto whatever you ranked it. And if it's in the correct form, one of these models should map on after you do the ranking, and that would tell you whether or not you have an R or an S. So first you need to make these, make sure they're correct. You do the rankings correct. And then you map on whatever you ranked onto one of these, and whichever one fits, it aligns correctly. Right? In this case, it would be red going up, blue going away, or white to the right, green coming at you, blue going away. Whatever one of these matches up, that's the right RS configuration for that asymmetric center. Practice, practice, practice. We will continue to work on this and practice multiple times in class, lots of opportunities. This is just the start, so keep practicing, and we'll keep doing it more in class as well.